Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to the subject of Machine Design 1. We are right now in the module number 3 where we are learning design of the parts which are facing static loads, that is design against static loading. The first part that we have considered is Cotter joint. In a last lecture we have seen what is a Cotter joint or what are the joints and why they are used, right? That's why we use them for connecting the shafts for power transmission. So in last lecture we also saw a sample example how to solve a design problem. In today's lecture we are going to look at what are the design aspects of Cotter joint and how the failure occur in them. In the next video we will be looking at how to solve the numerical of design of Cotter joint. Let us start with the design aspects of Cotter joint. So as you see, Cotter joint is a kind of joint, or there are many types of joint. The only common thing is Cotter inside them. Cotter is a machine element which is made up of either metal or woods. For our simplicity purpose, let us consider it is made up of just metals. So Cotter is this kind of shape which has a straight edge and which has a draft. Draft is an inclined edge, so that it can be inserted easily inside any cavity. So it's basically a kind of pin which is inserted inside the holes. The only thing is the shape of this is not circular, it is quite different, and that depends upon the given design aspects. So the Cotter is the important link. Then they say Cotter joint. So there are two more elements required for Cotter joints. One of them is called socket, another one is called spigot. Socket is something which has got hole inside. Spigot is something which has got the extruded part inside. The extruded part of spigot is going to be inserted inside the socket part of the socket. Once they are inserted, we will make a provision, or the provision is made in such a way that there will be cavities inside socket which will exactly match with the cavity inside spigot. Now the provision is made in such a manner that one side of the cavity in both of them will be straight, vertical of course, and the opposite side of that cavity will have some draft. Now this draft will be made in such a way that the insertion of this Cotter will be very simple in that case. I hope you are getting the problem. So when we draw the cross section of socket, spigot and Cotter joint, it looks like this. This is the socket part, inside which this spigot part has inserted. This is shaft 1, this is shaft 2, and the cavity that they have in common in this way is coincided, so that the Cotter joint can be inserted inside it very easily. If you see, it is acting as a locking mechanism. Since it has a draft, it can't go beyond that, right? So once it is fitted properly, it will fix the joint properly. So it's a locking mechanism. So once the locking mechanism is done, we can attach the first shaft to the motor and second shaft to the machine, and that is how the transmission provided by the motor will be transferred to the transmission of machine, and that is how the machines act. So this was the important relation between the Cotter and spigot joint. Now why I am discussing this? See people, whenever you have to design some product, you have to see how is the functionality of that product. Depending upon the functionality of the product, we will get the idea of failure mode of that product. And since now we know the functionality of this particular thing, we can define the failure mode of the product, that is Cotter spigot joint. So basically there are three parts that we need to design, that is socket, then comes the Cotter, and then comes the spigot. So when I say I need to design a Cotter joint, I need to design socket, Cotter and the spigot separately. So that is what the design of the Cotter and socket spigot joint. Let us look at the important formulae that are used. So let us begin with the spigot end. We know that spigot end is going to be attached with the machine. It can be done vice versa also, doesn't matter. So what we know is, before we proceed, we will name. So let us name these parts which are common parts. We'll call this part as the rod of spigot. This will be called rod of socket. This particular part will be called as flange of socket, and hence this will be called as flange of spigot. This is basically the cavity, or we'll call Cotter of the socket and Cotter of the spigot, and this is the main Cotter that we know. This basically already are called shafts. So with respect to this nomenclature only, we are going to define them. Let me quickly repeat: shaft of the socket, rod of the socket, which is this whole structure. This particular thing is the flange of the socket. So this will be the thickness of the flange, this will be the length of the rod. See, depending upon the appearance of the object, we need to define its dimension. For example, this part is very small, so we'll call it thickness, whereas this part is having certain length, that's why we'll call length of the rod. On the same way, it's the Cotter. Different dimensions of Cotter will be specified afterwards. So this is the rod part of the spigot, the lengthwise. This is the Cotter of the spigot, or the cavity of the spigot. This particular structure is the flange of the spigot, and this is the shaft of the spigot. Let's move ahead. So the formula we are writing about, the first formula of spigot end is diameter of the rod. So basically it is that upper portion, or it is the earlier portion of the rod which we are considering as far as the spigot joint is concerned. So that is given by, if we take the cross section, it looks like this. So this diameter we need to define, and hence it is called as diameter of rod, or you can say, we can just write it in terms of formula, the force, the load which is acting on that, P. Now we know that the load acting on this will be the tensile nature, because as the assembly is done, the only way of failure is in this manner, right? One of the ways will be like this. So in that case, the load applied is in tensile manner, and hence tensile force will be given by pi by 4 diameter square into the stress that acts on the body. Now this is going to be the direct stress, so we'll use the letter sigma for this direct stress. So where we unknown will be small d. P value and sigma values will be given. Let us move ahead with the next dimension, and that's called diameter of spigot and thickness of the Cotter. Now it is the spigot diameter that we are concerned with, and the thickness of the Cotter which we are concerned with. The formula says that, now we again know that this part also is going to fail under tension, so we have to consider the tensile failure, and the formula says that, again, the axial load is equal to, whenever it's a failure in tension or compression, we have to consider axial loading. P is equal to pi by 4 diameter 1 square minus diameter 1 into T. So we are discussing about the diameter of spigot, where this is the part which is area, right? Area which is actually responsible for the spigot, into this stress. Now again we are considering the axial stress, sigma. So that is what the formula we are going to use to find out the diameter of spigot. So here also the unknown parameter is going to be spigot diameter. We have mentioned this diameter of rod by letter D. We will mention spigot diameter by D1. So these are the two formulae associated with this spigot. The third formula which comes up is the thickness of the spigot or collar or cotter of it. So that goes it. Now you need to understand that the cotter part, which we already have seen, this cotter part is going to fail under the crushing. Crushing is something which is closely related with the compression. So this part of the spigot of this part of the cotter of the spigot is going to fail under crushing. So we need to consider the crushing load for it. Crushing load is a kind of compressive load, and therefore when we need to define the, or we need to decide the later the dimension T, thickness, we need to consider this formula of thickness, which says that the axial load is given by D1 into, where D1 is nothing but the diameter of spigot, into thickness T into sigma B. Sigma B is nothing but the crushing stress. So here unknown is going to be T, thickness. Let's move ahead with the next formula. Third formula of spigot, that's the length of rod. Length of rod of spigot. It is given by axial force is again equal to twice the diameter of spigot into length into the stress that we are going to consider. So stress value is going to be shear stress. Now you need to understand one thing. If we consider the length of this particular spigot, we are going to consider the cotter failure in terms of shear, and that's why we have considered shear over here. The fourth formula comes up for the outer diameter of flange or collar. Flange or collar is one of the same thing. So we know that this part which we have called flange is also kind of collar given for that particular element. So to find out the collar diameter, we know that collar diameter is also going to have a rupture, and hence it will be defined in terms of P, the acting load, is equal to pi by 4 the outer diameter square minus inner diameter square into crushing or crushing stress, where unknown here is going to be outer diameter D2. So using this formula, someone can go for the design of spigot. Let's move ahead with the last parameter of spigot, that is the thickness of collar, spigot collar. Now this is the thickness which is across this length that we are going to consider for collar. So this thickness we need to consider. So the formula again says that P, which is the axial load, is equal to pi. Now when pi comes into picture, it is something that is related with the circumference, right? So it is pi d1 t1 into tau. Again, the reason is it is going to fail under shear when we consider its thickness, where the unknown will be T1. So these are the important formulae that are used for spigot joint design. Let's move ahead and go for design of socket end. To consider the socket end design, we are going to consider outside diameter first. So it is outside diameter. The first one is of socket end. So when we define why outside diameter is important, because we know that in socket end there is going to be a hole, and that's why we need to consider the outer diameter and the inner diameter. So for outside diameter, we know that again the failure is going to be the axial load, because of the axial load. So it is P, the acting load, the axial load is equal to, it's about the area. So area for the outer, considering the outer diameter, d3 square minus d1 square. Now we know that d1 is the diameter of spigot minus d3 minus d1 into thickness t into sigma in tension. So here your unknown will be d3. Our next formula is for outside diameter of collar of the spigot end. Sorry, outside diameter of the collar of the socket end. Now we know that collar is the extremist part of this particular component, and hence it will be given by, it also is considered to be failing under shear. So it becomes P, which is the actual load, is equal to d4 minus d1. Now this is the difference between the outermost diameter and the innermost diameter into thickness, because that is the projected area, and into sigma b, which is the rupture stress or crushing stress. So here our unknown is going to be d4. So this was the second formula for socket end. Let's move ahead with the third formula, which is very important. It's called thickness of the socket collar. Now this thickness is again defined in terms of shear failure. So it is given by the axial load into twice of the extremmost diameter minus the innermost diameter into its thickness. Now this thickness is the thickness of the collar, which is on the socket end, into shear stress, because we know that it is going to fail under the shear. So this is what the third formula we have for the socket end. Let us move ahead with the fourth dimension, fourth and the last dimension as far as the socket end is concerned. It is about the thickness. So it is the thickness of the rod or thickness of the socket near rod. So that failure is going to be again the shear failure. So the formula is given by, your axial load is given by pi times the diameter into its length into shear stress, which is generated inside it, and the length is going to be the first length. So that is the end of formula list for socket end. The last component which is left over is called Cotter. The Cotter which is going to be inserted. So the dimensions for Cotter. Yes, Cotter can be redrawn in terms of, the Cotter can have variable shape depending upon the application, but the in general shape of Cotter which we had drawn before with a straight edge and with a draft edge can be drawn in the form of 3D like this. When we are going to insert the Cotter is going to fail in 3 different ways, in 3 different sections. One part of the section is going to be dragged in one direction, another part in opposite direction, and the remaining part in the same direction as that of the previous. So when this Cotter is going to fail, it is going to fail in this way. This will be dragged in this way. Another thing will be dragged in this way, and the last part will be dragged in the opposite direction. So that is how the Cotter is going to fail. So Cotter is going to fail mainly because of shear. So shear stress is very much important as far as the failure of Cotter is concerned. So let us define some of the dimensions. For example, this is going to be the thickness of the Cotter, which is going to be uniform throughout its height. Then let's consider that the middle portion has the depth of say d1, so that the upper and lower depths can be decided accordingly. We'll call that this is the width, that is b1, or we'll say b1, and this width is called b2, so that the middle width can be taken as their mean and will be called as b. So when the dimensions are concerned, the first dimension comes to this, that's called mean width of the Cotter, this b factor. So mean width of Cotter B is given by force P is equal to, we know that we are going to take mean of that, so B1 plus B2 is going to be the factor into the thickness. Now this is basically the projected area, into the shear, because we know that it is going to fail under shear. So here unknown factors will be B1 and B2 that we are going to find out. We also know that P is equal to twice the length B, because it's a mean length, because that is substituting the B1 and B2 factor inside, multiplied by thickness into shear stress, and that is how we can find out B, which is mean width. In some cases they may ask us B1 and B2 with certain relation. There will be certain relationship between B1 and B2. Once we know B, we can find out B1 and B2 also. The second and the last formula that we are going to use for Cotter dimension is, we need to consider, or we need to check whether the Cotter is going to fail under the given load or not, and for that it's called checking the Cotter under bending or bending stresses. We know that this Cotter is going to have certain length, and the loads acting are transverse to this. Whenever there is some member which experiences transverse loading, it is possible for it to sustain the bending stresses, and that's why we need to check the bending failure for this particular Cotter. And therefore maximum bending stress will be given by Now there is some theory that we are going to use. Based on that theory, the formula is derived, so we are going to apply it directly. So it is P divided by 2 inside bracket d1 by 2 plus d4 minus d1 divided by 2 into 1 by 3 minus p by 2 into d1 by 4. That's a standard formula which we are going to use. There are certain references. Hereafter we are going to use the references from PSG data book. PSG is the publication name and it provides us the data for different kind of materials. It's a standardization. So for next problem onwards we are going to use that formula. Right? So this is the list of formulae, which is quite lengthy, which we are going to use for designing of Cotter joint. In next video we will solve a numerical based on design of Cotter joint. So this was from my side. Thank you for watching this video. If you like this video, please subscribe to Ekeeda. Thank you.